പോണല്ലോ.
ആയിക്കോട്ടെ.
ഇതേപോലെ ഇപ്പൊ
ടീച്ചർ ഇപ്പൊ ഫ്രീ
I don't know what is happening. I'm not able to share the slides. Let me try once again. I'll just leave and join again. Okay, something is wrong with right now. I was able to see everything in the morning, but right now it's not working properly. So I'll start with a blank presentation. Can you see the blank screen slide?
Yes, ma'am.
Okay, we'll start with this. It's really unfortunate because I had kept everything ready. Okay. So yesterday, in one class, I had discussed A batch. I had discussed something about the biasing and all. I'll have to repeat it right now. So A batch students, kindly bear with me. So bias. So let us consider this a load line. So when you have a load line like this, it is called the DC load line. So you have voltage, collector emitter voltage on x-axis and collector current on y-axis. So for this, the first on the basic circuit we can consider is a fixed biasing without emitter resistance. Okay. Later on, we'll introduce the emitter resistance. So this is the circuit. So you have collector resistance and RB. So from VCC, current can flow through RB and through base emitter junction, so that the equation will be equal to VCC is equal to IBRB plus VBE. Please remember that this current is a DC current. That is why capital I is used. And the next one is IC into RC plus VCE. Okay. So when this happens, you can have the no.
Yes, miss.
I don't know what is the issue.
മിസ് ഷെയർ ചെയ്തിരിക്കുന്നത് പ്രസന്റേഷൻ വിൻഡോ അല്ലാതെ PPT ആ പവർ പോയിന്റിന്റെ വിൻഡോ ആ ഷെയർ ചെയ്തിരിക്കുന്നത്. സ്ക്രീനായിട്ട് പ്രസന്റ് ചെയ്താൽ ചിലപ്പോൾ ശരിയാവും.
അല്ല അത് വെച്ചിട്ട് എനിക്ക് ഓപ്പൺ ചെയ്യാൻ പറ്റുന്നില്ലായിരുന്നു. അതാണ് ഞാൻ ഇതിലോട്ട് മാറിയത്. നോക്കട്ടെ ഒന്നും കൂടെ. കാണാമോ? സ്ക്രീൻ കാണാമോ?
Yes, miss.
Let me try again. Okay, so we are ippada.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, so let us consider a fixed bias circuit. Fixed bias circuit, you have VCC, then two resistors, RC, RB, and transistor. So current can flow, start from VCC, it will flow through RB and through the base emitter junction. So that the first equation is VCC is equal to IBRB. See, I am using capital I to indicate that it is DC current, and plus VD. And the next equation is it can flow through the collector and through the transistor. So it is equal to VCC is equal to IC into RC plus VCE, where VCE is the drop across transistor. So now transistor can operate in three regions, that is active, cutoff, and saturation. All this we know. And you have two junctions, that is emitter based junction and collector based junction. When the transistor is in active region, emitter based junction is forward biased, collector based junction is reverse biased. And in cutoff, both are reverse biased. And in saturation, both are forward biased. Okay. So these two seems to be the extremes of transistor operation. So when the transistor is in cutoff, it means both junctions are reverse biased and no current can flow through the transistor. So you have an open circuit across the transistor, and therefore the collector voltage, the voltage between collector and emitter, will be equal to VCC itself. So if you plot, you will get one extreme, that is VCC. That is a cutoff point. Now, the other extreme condition is saturation, where the transistor is in emitter-based junction and collector-based junction are forward biased. So when they are forward biased, the transistor is acting as a short circuit, so that entire voltage is dropping across RC. So in this equation, you can substitute VC is equal to 0, so that VCC is equal to IC into RC, or the current is equal to VCC by RC. So that is the other extreme. So joining these two, you can get a straight line, and it contains all possible conditions. So the active region is slightly forward biased, or it is in deep forward bias condition, and operating point can be located anywhere. So this basically indicates the DC load line. Okay. But here you find that we have not included any AC signal. We have just examined what is happening when the transistor is given a DC voltage. Now, when you are giving an AC signal, we will be giving an AC signal. Suppose I am giving AC signal directly to the base. Then what will happen? From VCC, current can flow through RB, and instead of flowing to the transistor, it can flow to the circuit. That is the AC source. Likewise, if I'm taking output directly from collector to the load, then also the same thing can happen. And another thing is, so here some AC signal can go from the base, from the external to the other DC supply also. So anyhow, you require a coupling capacitor. All this we had discussed earlier. So that is coupling capacitor. At the output side also, you might require a coupling capacitor. So when this coupling capacitor is included, and now you are connecting the load resistor, RL. Okay. So what we have done is, we have connected, this is the load where I require the output of this amplifier, and instead of directly connecting it to amplifier, I have connected it to through coupling capacitor. So when this happens, for DC conditions, the capacitors are open circuit, and so this RL will not be present. Whereas when you have so when you have this coupling capacitor for AC connection, it acts as a short circuit. And what are the rules for AC analysis? AC analysis, can you tell me the rules? Capacitors are short circuit, isn't it?
Yes, ma'am.
And DC voltages are grounded. So these two are the main rules for AC analysis. So when you do this VCC will become grounded. So it will be grounded. Then what will happen is from collector, you will have RC coming to the ground, and at the same time, this coupling capacitor is a short circuit. So from collector, RL is also grounded. Okay. So in effect, you can redraw the circuit as you have a ground here and RL like this. So RL and RC are here. Therefore, this can be represented as RL and RC coming in parallel. So whenever you have a load resistor connected through a coupling capacitor, then the result is RC and RL will come in parallel. So now when you write the equations, how can we write the DC, the output loop? When you write the current path for at the output side, this VCC is 0. VCC is 0. So what you get is 0 is equal to AC current is small IC into RC parallel RL plus VCE, or IC is equal to VCE divided by RC parallel RL. Okay, and so you are going to get another line like this, which has a slope of minus 1 by RC parallel RL. And this RC parallel RL is denoted as small rl. Okay. The small letters are normally used for AC analysis. So the small r L stands for RC parallel RL. Okay. And this line is known as AC load line because that will come into effect only when AC signal is there. And the intersection of DC load line and AC load line is the operating point. So operating point is denoted as VCEQ, and this is the reference point for our output. Okay. So we can draw like this. That is the output. So if only AC signal was there, then we would say that with respect to on this quiescent point or the operating point, our output signal can increase up to VCC because that is the extreme here. This is the reference point and output can reach up to VCC. Theoretically also that is possible. But practically what happens is you are, because this AC load line is ending at an earlier voltage, your AC signal is limited till there. So this is the maximum swing you can have. So this is equal to AC current IQ into RL. So IQ into RL. So that RL determines what is the voltage here. Okay, that we'll see later on also. So that is the difference between AC load line and DC load line. Now let us consider if you are introducing emitter resistance also. Okay. Earlier we considered a fixed bias without emitter resistance. So you have fixed bias circuit RC, RE. Okay. Now, if you try to draw the load line, now what is the difference? When the transistor is in cutoff, again, the transistor acts as an open circuit. The resistance is very high. Open circuit means it's infinity. So compared to infinity, so when you measure the, if you measure the resistance from collector to emitter, it is infinity plus capital RE. So you don't bother about it. And we'll say that the entire voltage, the open circuit, you are getting at the collector point. So that is VCC. And what is the maximum current when the transistor is a short circuit in saturation? When the transistor is in saturation, it acts as a short circuit. So no voltage is dropping across it. But now, compared to the earlier circuit, you have an additional resistor where voltage is getting dropped. So you'll have to write as VCC is equal to IC into RC plus RE plus VCE. Now VCE is 0 for saturation. So the point is now VCC by RC plus RE. Okay. And the slope of so that is the DC load line. So the slope is now 1 by RC plus RE. What was the slope for DC condition here? It is equal to 1 by RC. Okay. So this is the slope. Now, to give AC signal, most often you connect a capacitor in parallel to this, and so you have an option. If you want, you can connect a capacitor, bypass capacitor. That is not compulsory, but what we normally do is you will have a capacitor so that gain is enhanced. So we can consider both conditions. You have input coupling capacitor, output coupling capacitor, load RL, and if you want, you can connect. If you are not connecting RE, parallel capacitor across this, now what will be the equation? Here, as in earlier case, for AC analysis, this becomes a capacitor, becomes a short circuit, VCC is grounded, so RC and RL will become parallel. Okay, RC and RL will become parallel, and current will be flowing like that. But when you don't have a capacitor here, some current will be flowing through capital RE also. So that also you have to take into account. Suppose I'm connecting a capacitor like this, bypass capacitor, then for AC analysis, this circuit will be modified as, for AC, you have you don't have capital RE, because that becomes a short circuit. Capacitor is short circuit. So that will not be there. So what you have is emitter is directly grounded and collector is connected to ground. Collector resistance is connected to ground and RL is also connected to ground like this. So we have the earlier situation. Current will increase and voltage ends early. So you have an intersection, that is Q point, and the slope of this line is now, instead of 1 by RC plus capital RE, it is 1 by RL. Okay. What is RL? So look at the difference. Where for DC, this RL was not there. That is why the slope was equal to minus of 1 by capital RC plus capital RE. And in case of AC analysis, this capital RL will come into effect. So the slope has now changed to 1 by small rl, where small rl is equal to RC parallel RL. Okay. So this is the difference between AC load line and DC load line. So the points you have to remember is operating point is the intersection of AC load line and DC load line, then the slope of these lines are different. And because the AC load line is ending early, it will be equal to AC current into this small RL. That is the magnitude that is possible here. So our swing is now reduced. If you consider only the DC load line, you can have a swing from 0 to VCC. That is how we considered for power amplifier. When you discuss the maximum efficiency, we considered that the sweep is from VCE max is VCC and minimum is 0. But in practical situations, when you consider the AC load line, the swing is reduced. So to find what is the maximum input you can give, you have to consider this condition. That is from operating point till where the AC load line ends. And that will be equal to AC current into, that is the quiescent current into RL. So that is the point. Now what happens? So you have designed everything like this, but now what happens is when there is a change in temperature, suppose you are changing transistor. Transistor is, first transistor was having beta 1 and then you change it to beta 2. Then definitely collector current will vary. It can increase or decrease. So what will happen to operating point? Operating point will shift. So you had earlier designed for exact middle low of operating load line so that you are getting maximum undistorted output. But right now, because the transistor is changed, the operating point can shift. That is one possibility. Now, the second possibility is when temperature changes. When temperature changes, beta is a function of temperature. So beta can vary. Okay. Beta will change. Then the reverse saturation current, ICO. Okay, I'll tell you what ICO is. That is the reverse saturation current. Right now, just consider it as ICO. Then the base emitter voltage can also change. Now, what is ICO? If you have a transistor with emitter, base, and collector, emitter base junction is what we normally look at for forward bias, because that is forward bias condition and that determines how many carriers are crossing to the collector. So what we are interested is how many carriers have started from emitter base, forward biased emitter base junction, and how much is reaching there. So here you have base current and it is getting multiplied by beta. And so this base current is entering here. So many carriers are coming from the emitter region. This will determine what is the beta, that is transistor dependent. So according to beta, you will get collector current. So we'll write as beta IB. But in reality, what happens is this collector base junction is reverse biased. And reverse biased junction means there will be a small, so let us say this is NPN. There will be a very small minority carrier crossing happening because of the reverse bias. That means electrons will go from P to N and holes will go from N to P. So that reverse current will happen there. So we'll consider the reverse current that is happening at the collector base junction. And this O stands for, when we are analyzing, looking at the reverse saturation current or the leakage current at the collector base junction, you keep emitter open. So you are not giving any bias to the emitter junction, and we are looking at what is happening at the collector base junction. So that is called ICBO, and usually it is denoted as ICO. So the total collector current that reaches the collector terminal. So imagine this collector base junction. You have electrons are the minority carriers in P region. because of the reverse bias, maybe 2 or 3 electrons are crossing to the collector junction. So they are also contributing to the total collector current. When we consider only the current amplification due to base current, we neglect the reverse, the minority carriers crossing to the collector junction. So if you consider that also, then the equation becomes beta IB plus beta plus 1 ICO. Okay, where ICO is actually ICDO. Now, sometimes this everything together is also denoted as ICEO. So you are considering it in the emitter mode. Then you don't have this beta plus 1. Okay, so this is the actual equation of collector current. So here you can see that this reverse current, even though it is very small, it is getting multiplied by beta. Beta is usually in the range of 100 to 400. So a little significance is there for the reverse current also. If you measure the current exactly, so that can be seen from the output characteristics. When base current is small, the carrier will be in the
മറ്റേ നേരത്തെ 1 ഉം 2 ഇട്ട് പറഞ്ഞില്ലായിരുന്നു, അത് എന്തിന്റെ റീസൺസ് ആയിരുന്നു?
ഏത് 1 and 2?
ഈ മോളില് beta 1 beta 2 IC increase.
When you are changing transistor, the first transistor, you are designing a circuit, amplifier circuit. So for that, fixing the operating point, I'll take current is equal to say 2 milliampere. Okay, and to find what is the biasing resistor RB required to get IB, I will have to consider beta. Say I'm taking beta is equal to 100. Okay, so I'll be fixing this resistance RB, say 100 kilo ohm, maybe 100 kilo ohm, so that I'll get 2 milliampere collector current. Okay, that is under the assumption that beta is equal to 100. Now, after some time, the transistor is damaged and replacing it with another transistor of beta, let us say 300. What will happen? This RB is fixed so that the base current is now changed. Sorry, base current will remain constant because this RB is fixed. What was the equation? VCC equal to IB RB plus VBE. Okay. So as per this equation, if RB is not changed, then IB will remain constant. So if IB is 10 microampere, then it will be the same. Or if you consider the earlier condition, 20 microampere. So 20 microampere with a transistor of beta 100, I'll get 2 milliampere. But now the second transistor is having beta 300. What will happen? 20 microampere is multiplied by 300, so that now the collector current is 6 milliampere. So it will be in saturation. Okay.
Okay.
So that is a troublesome condition because you wanted the transistor to work as an amplifier. But right now it is in saturation, means it cannot work as an amplifier. It can work only as a switch. Okay. All right. Now talking about this reverse current, if base current is small, the slope of this output characteristics is not significant. But as we increase base current, you can see that the output characteristics of common emitter is changing. The slope is entirely different. Okay, so let us say what you need to understand is I am plotting the base current for 20 microampere. So at 20, my IB is equal to 20 microampere. When the voltage applied across the transistor is 5 volt, I'm getting only this much current. This is the collector current, IC1. But when I increase that to 15, now the current has changed. My input current has not changed. But because a large voltage is applied, temperature across that junction is changed. Okay, that is the main thing happening there. When large voltage is applied across the transistor, power dissipated across the transistor increases. That means the temperature across the transistor increases, and reverse current, ICO, can change. ICO changes means there is a sudden increase in the second component and your collector current is changing. Okay. So then also the shifting of Q point can happen. So that is the problem of ICO. And beta is also temperature dependent. When temperature changes, beta can vary. That will also change the operating point. Now the base emitter voltage is also slightly temperature dependent. So here you can see that for every 10 degree, this is applicable for most of the semiconductors. For every 10 degree rise in temperature, doubling of ICO will happen. Okay. So when you consider germanium and silicon semiconductors, germanium has minority current or reverse saturation current in the range of microamperes, and silicon has in nanoamperes. So you can see that germanium is more temperature sensitive because the variation in reverse current is much larger than what is happening in silicon. So for germanium transistors, this variation is the most significant one. And for silicon, this base emitter voltage variation can happen. That is very small. For every doubling of temperature, you can get a variation of 2 millivolt across the base emitter junction. So this is more critical in silicon. For silicon, VB is the critical one, and for germanium, it is ICU. So anyhow, these problems, variation in beta, variation in reverse current, variation in forward bias voltage VB, all the three can shift operating point to another location, which will result in either the circuit is no longer working as an amplifier or it is getting clipped. So that also I think we had discussed earlier, but again, let us see once more. So let us say this is my operating point. Okay. So when that is my operating point and applying a voltage here, input voltage, so that will produce corresponding base current and it will produce a larger collector current like this. So you can see all are in phase. Okay. Input voltage causes base current variation in the same manner, and IB and IC are in phase. So the same variation can happen. But the voltage will be, what will happen when you have positive half cycle for the current, you are going to get a negative half cycle, and then you get a positive half cycle during negative one. So if there is a shift in operating point, let us say the operating point is changing to near cutoff, what will happen? Positive half cycle will be clipped, because this is the maximum possible voltage here. So your operating point is fixed, operating point is shifting here means you can have negative half cycle as such, but the positive half cycle will be clipped. And if your operating point is coming near to saturation region, then you don't have space for the negative half cycle. You can have positive half cycle undistorted. So when you do an experiment, if you find that one side is, that's a shortcut to understand whether your operating point is at the middle or not. You increase the amplitude of input signal. If one side is getting clipped, it means your operating point is not at the middle. Whenever we design an amplifier, we take VCE is equal to VCC by 2, 50% VCC. That is the typical design approach. So we expect the operating point to be at the middle. But after wiring, if operating point is not at the middle, when you increase the input amplitude, you find that one side is getting clipped. And depending on whether negative half cycle is clipped or positive half cycle is clipped, you can understand whether the current is more or not. Say I'm designing for 2 milliampere. If I find the negative half cycle is getting clipped, it means that my quiescent current is much larger than 2 milliampere. And if my positive half cycle is getting clipped, it means the current is less than what I have designed. So then you can change the values of R1 and R2 or when I say you can vary R1 and R2, what is the meaning that when R2 is changed, I can increase or decrease the forward bias of base emitter junction. And by controlling the forward bias of base emitter junction, I can control base current, which means I can control collector current. So if I want to increase collector current, then I have to increase base current, which means I have to increase the forward bias of base emitter junction. So R2 has to be increased. And if I want to decrease collector current, I can decrease R2 a little bit so that the forward bias of base emitter junction will decrease and eventually collector current is reduced. Okay. Sorry. Okay. So once you have designed this amplifier, you don't want the operating point to shift. That is known as bias stabilization. So you are keeping your biasing condition stable. And how much stable is it with respect to variation in beta, variation in reverse saturation current, and variation in VBE? Just a minute. Okay, so for that we define a stability factor. So stability factor, we will be observing what is the variation in collector current. Now we have seen that collector current is a function. It can vary according to beta, ICO, and VBE. Actually, we'll put ICO as the first one because that is a main factor. Then we have the change in VBE, and then you have beta. So S means it is equal to, another way of representing it as SI because it is with respect to ICO. Dou I by dou ICO. Now partial differentiation is used because all these three are variables. Now here we assume that beta and VB are constants. Then you have S dash. S dash is equal to SV is equal to dou IC by dou VBE with beta and ICO constant. And the third one is S double dash, which is equal to S beta is equal to dou IC by dou beta, keeping ICO and VBE constant. So from the equation, you can see that if value of S is large, it means collector current is varying to a large extent. So that means the circuit is not at all stable. You can't depend on the circuit, because on day one it will be perfect, but after 2 or 3 days it is going to malfunction. So S increases means stability increases. So the actual stability of the circuit and the factor S, stability factor, are inversely proportional. Stability factor actually indicates how unstable your circuit is, and the maximum or the minimum, if S is minimum, then your circuit is better. So you will try to minimize S as possible and make it tending to 1. So that is our aim. So we have to examine how each circuit will behave with respect to the variation. So the first circuit we consider is fixed bias circuit. We'll consider without capital RE first. Okay. Then we write the loop equation. So VCC is equal to ICRC plus VCE. Then VCC is equal to IBRB plus VBE. Now this VBE is much smaller compared to VCC. So I can approximate this as VCC is equal to IBRB, or IB is equal to VCC by RB. So that is a constant current, as that is why the circuit is known as fixed bias. Fixed bias means the base current is fixed. It is not depending on the transistor or its beta. It is due to the circuit, it is giving a base current of VCC by RB. Now, what is the total collector current, general collector current equation? It is equal to beta IB plus beta plus 1 into ICU. Okay. So substitute this, beta VCC by RB plus beta plus 1 ICU. Okay. So when you take dou IC by dou ICU, it will result in beta plus 1. Okay. That means the circuit is highly unstable because the beta which varies from 100 to 400. So the fixed bias is having a stability factor S is equal to this much. Now let us try to include emitter resistance also. Now what is the significance of this emitter resistance? Can somebody tell me? How this emitter resistance is functioning? Why we connect emitter resistance? Please tell me.
To counter thermal runaway.
Okay. Okay, correct. That means it is controlling RCRE. Okay, let us consider. Basically, this is if you write the equation for IB, it is equal to VCC equal to IBRB plus VBE plus IERE, because the path is from VCC, current is flowing through RB, then through the base emitter junction, and through RE it is coming to the ground. And IE is equal to, what is IE? It is IB plus IC. Okay. So if I take IB alone here, it is equal to RB plus RE plus VBE. You can neglect VBE into ICRE. This is equal to VCC. So what is IB? IB is equal to VCC minus ICRE divided by RB plus RE. So IB is equal to VCC minus ICRE divided by RB plus RE. This equation will help you to understand what is the significance of this emitter resistance. In earlier situation, due to some reason, if there is a change in current, then let us say you are changing. There is a change in collector current. Now, when collector current changes, this numerator changes. Collector current is increasing due to change in ICO or beta variation or base emitter voltage variation, whatever be the thing. If it is increasing, then the numerator will decrease. And numerator decreases means base current is reduced. When base current is reduced, eventually collector current will be reduced, because anyhow collector current is equal to beta times IB. That factor is there, plus beta plus 1 ICO is there. But because of this factor, if there is a decrease in collector current is brought down. So this equation is enough to describe all the advantages of emitter current. In earlier fixed bias, without capital RE, what was the equation? IB is equal to VCC by RB. Okay. So IB is a constant that is not changing. Whether collector current is increasing or not, base current will remain the same. Whereas here you can see that there is a sort of feedback is there. Base current is not constant. If collector current increases, base current will decrease. And suppose collector current decreases, then the numerator will increase. Numerator increases means base current will increase. Base current increases, the collector current will increase. So whatever variation happens to collector current, the similar opposite variation, that is collector current increases means it will bring base current reduces. So base current reduces, so collector current decreases. So this happens in a loop. So what will happen? IC is constant. It is almost constant. Okay. So that is why this emitter resistance is said to be the stabilizing, thermal stabilization. It is said to give a thermal stabilization to the circuit. Now, so it is also known as self-bias. I just want you to be familiar with this term. So self-bias circuit means it will contain this capital RB. Okay. So it can be, RB can be like this, or this side can be voltage divider bias also. Anyhow, this emitter resistance will introduce a self-bias condition, which means automatically the circuit is doing a regulation so that the operating point variation is nullified. The change in collector current is nullified. Okay, so please try to get the equation for S. Substitute this IB in this equation. Do it. What do you get? IC is equal to beta into VCC minus ICRE divided by RB plus RE plus beta plus 1 into ICU. Now take the IC term to the other side. So it becomes IC into 1 plus RE by RB plus RE into beta is equal to beta VCC by RB plus RE plus beta plus 1 into ICU. So what is S? S equal to dou IC by dou ICU is equal to beta plus 1 divided by beta into RB plus RE 1 plus RE by RB plus R. Is it correct? Please tell me. Did everybody get this? Did everybody get that? Okay. Why don't you speak? How will I understand? So I can rewrite this. 1 plus beta into the denominator will be RB plus RE plus R. Okay. So here the stability, this factor has now reduced, isn't it? So stability of self-bias is better than the other one. Now coming to voltage divider bias, let us see what happens. In voltage divider biasing, the circuit is like this. You have again voltage divider biasing means normally we don't connect it without capital RE. This circuit can be modeled as, you consider that the equivalent, Thevenin equivalent, you can consider it as RBB and VB, where VBB is equal to VCC into R2 by R1 plus R2. And RBB is equal to R1 parallel R2. Okay. So this circuit is equivalent to having a fixed bias with two power supply. Fixed bias, you can have different. Here, VBB, RB, VCC, RC, RE. So fixed bias with emitter resistance and the equivalent of a voltage divider biasing are similar. Now, what is the significance of voltage divider biasing is you are keeping the voltage constant here. Voltage across R2 is always equal to VCC into R2 by R1 plus R2. If you look at the earlier equation, consider this equation. That is the first one, VCC is equal to IBRB plus VBE plus IERE. So if I try to write what is VBE, it is equal to VCC minus IBRB minus IERE, and IE is nothing but IB plus IC. So if there is a variation in this current, then the base emitter voltage can change. Okay, so that is something and you don't want, because you want the base emitter junction voltage also to remain constant. Remember, I told you the variations are collector current can vary when there is a change in base emitter voltage or change in reverse saturation current or change in beta. So we have not considered the change in beta as of now, but the first one we have considered, and the second one is the change in VBE. So as per this equation, this base emitter voltage is not a constant. So what we are trying to do in forward voltage divider biasing is, when you connect a voltage divider, when you connect R1 and R2 as a voltage divider, then the middle point voltage, that is always equal to VCC into R2 by R1 by R2. So it is a ratio of resistances. And semiconductors are more prone to temperature variations, and resistors are more, for normal temperature variations, they are immune to that. So, and also you have a ratio of resistance. So that means when there is a change in resistance due to temperature in the numerator, you will have a similar change in the denominator. So that gets cancelled. So this will be stable. That means the base voltage will remain constant. Okay. When And how is this RE functioning? RE is functioning by keeping the base current constant. And to keep base current vary according to variation in collector current. Look at the earlier equation. This is what we said. IB is equal to VCC minus ICRE. Here we neglected this VBE, but if we include that also, then what we can say is, if base current is constant and due to some reason collector current is changing, then the voltage at emitter is changing. So that base emitter voltage will vary so as to decrease base current and bring back collector current to changes. Okay, so I'll summarize like this. When you include a voltage divider biasing, you have two advantages. One is capital RE will take care of variation in collector current changes. But if there is a change in collector current, that current flows through capital RE, and collector current variation produces a negative effect on base current. So base current will change so as to bring back collector current to a constant thing. The same thing happens when there is a change in base emitter voltage. Because one end is kept constant, the base voltage cannot change here in voltage divider biasing. So whatever variation is happening to the junction, that gets reflected at the emitter side. So that will again produce a similar change in base current, and base current variation will try to nullify the variation in collector current due to change in base emitter voltage. So voltage divider biasing is considered to be superior because it can take care of the variations due to reverse saturation current as well as this base emitter voltage variation. Now, suppose transistor is changed. That you can do we'll do that a problem in class later in offline mode, and then I can show that beta variation is also less affected in voltage divider biasing. So that is why voltage divider biasing is considered superior to all other biasing circuits. Okay. So S dash and S double dash, they are related to S. So if you bring down S, then naturally S dash and S double dash will also increase. This derivation we'll do in class. Okay, that also in offline mode. Otherwise, you won't do it now. Then we have something known as compensation. So what we discussed till now is stabilization, bias stabilization. Biasing means you are fixing the operating point at a desired point. You want the circuit to work as an amplifier, your operating point is at the middle. You want it to work as a switch, you are fixing the operating point either at a cutoff or saturation. So that is known as biasing. So bias stabilization means you are keeping the operating point where you desire. If you want it to work as an amplifier, you design it at the middle and keep it at the middle. So that is taken care of by additional resistors. You are connecting some biasing circuits to keep it there. That is known as stabilization. Now, what is the meaning of compensation? Compensation means in spite of doing this stabilization, due to some reason, there is a change in operating point. So how can you compensate for that? Just like if you have an acidic, you want a neutral solution, you find it is slightly acidic. So what will you do? You add a little base solution so that is compensated. So similarly, we have some situations. Say you have a circuit like this. Instead of R2, you connect a diode there. Okay. And see, according to the, when you connect a diode in reverse bias condition means this diode is now reverse biased. So it will be having high resistance. So you have sufficient forward bias at the base emitter junction. And only the reverse current is flowing. The diode is reverse bias means only the reverse current is flowing. So here you have some reverse current flowing, and similarly at the base emitter junction also you have, through the transistor also you have the reverse current flowing. So any change in that reverse current will be nullified by the change in this reverse current of diode, because both are made of same material. Okay, the transistor and diode are of same material. So any change in reverse current of transistor will be nullified by the change in reverse current of diode. So that is the diode compensation for ICO. So this particular circuit is for variation of ICO, compensation for ICO. Now if I put diode at some other position, what I'm going to do is add it to the emitter side. Okay. When I keep a diode like this, now here what happens is, through this resistance, external resistance, this diode is maintained in forward bias. So the forward bias, it has a forward bias voltage here. And what is the polarity of that voltage? It is minus plus. Whereas the base emitter junction voltage of transistor is with positive at the base and emitter at the emitter is having negative. So the diode drop and base emitter junction voltage drop of transistor are opposing, plus minus, minus plus. So any change in VBE happening at the emitter base junction of transistor will be nullified by variation in a diode drop, because again you are keeping the diode and transistor same type. So this is against variation of delta VBE. This is the compensating circuit for variation in VBE. And the first circuit is for variation in ICO. Now the third one is have a circuit. Now you are introducing something known as thermistor. Have you heard of thermistor? Thermistor, this is the notation. You put a resistor and put a round here. It is denoted as thermistor. Thermistor is having negative temperature coefficient, which means when temperature increases, the resistance will come down. And how does this work? See, normally when temperature increases, due to ICO variation on all, collector current is going to change. So when temperature increases, this resistance which is connected from VCC directly to emitter. Okay. So at normal condition, normal temperature, the resistance is very high. So it can be considered as open circuit and it will not affect the working of your amplifier. But when temperature increases, the resistance will come down, which means current from VCC, one part will flow through a transistor and another is flowing through RT, and then it is coming to RE. So you have a larger current flowing through RE, so that the drop across RE increases. Now, as we have seen earlier, when drop across RE increases, that reverse biases the base emitter junction. Okay? It is slightly, because you are maintaining the voltage at base constant. Again, the significance of forward voltage divider biasing. This voltage is constant. It is independent of transistor. So when there is an increase in emitter voltage, the forward bias of base emitter junction decreases. So base current decreases and collector current will reduce. So that is another compensating method. Okay, so that is for now. Just please don't leave. Let me take attendance. എല്ലാരും വീട്ടിൽ പോയോ?
Yes, ma'am.
Yes, miss.
ട്രെയിനിലാണ്.
ഓക്കെ ഓക്കെ. നിങ്ങൾ ഇവിടെ കറങ്ങി നടന്ന് ഇനി പനിയൊന്നും പിടിപ്പിക്കരുത് കേട്ടാ. ഈ 3-4 ദിവസം മാറി നിന്നാല് ഒരു പക്ഷെ എല്ലായിടവും, നമ്മുടെ ക്യാമ്പസിൽ മാത്രമല്ല എല്ലായിടവും ഉണ്ട് പനി. ഓക്കെ ഓക്കെ, താങ്ക് യു.
Thank you, miss.
Thank you.
Thank you, miss.
Thank you, miss.
Thank you, miss.
Q0 bar. This is Q0. So Q0 bar means 1, 0, 1, 0. Is that clear how I wrote the D1 in the state table? Okay. Now let me write D0. What is D0? XQ0. So since X is 0 here, this term doesn't appear when X is equal to 0. X bar Q1 bar. So X is 0 means X bar is 1. When X bar is 1, it is Q1 bar. Q1 bar means 1, 1, 0, 0. Did you get that? 0, so it is 1, 0, so here it is 1, 1, so here it is 0, 1, here it is 0. Here X is 1, so this term is gone. X Q1 bar is 0, X is 1, so it is Q0. What is Q0? 0, 1, 0, 1. Is this clear?
Yes, ma'am.
Can you hear? Can you hear me now? Okay. So did you understand how this D1, D0 is written?
Yes, ma'am.
Okay. So now I'll move to Z1. What is Z1? Z1 equal to Q0. So I'm just copying Q0 here, 0, 1, 0, 1. And Z0 equal to, what is Z0 equal to Q1 bar. So it is 1, 1, 0, 0, right? Is that clear for the Z outputs? Okay. Now to get the binary state table complete, we should get the present state and the next state, isn't it? Now we have formed only the inputs. So if you know the D inputs, what will be the next states? Since it's the D flip-flop, the next states will be same as that of the D input, isn't it? Since we are making use of the D flip-flop, the next states that will be formed will be same as that of the D input, right? So that means that this is equivalent to Q1 next and Q0 next. That's what we do when you do the design or the synthesis part also. The Q1 next and the Q0 next will be taken as D1, D0, isn't it? Same here. So now we are trying to write this is the binary state table now. We'll try to write the high-level state table. How did we come to the binary state table from the high-level state table while doing the design? How did we come to the binary state table from the high-level state table? We gave some binary assignments to the high-level names, isn't it? We gave binary assignments to the high-level names and substituted that binary assignments in that high-level names, isn't it? It's the reverse process model. How many states are there? 4 states. So we are going to give the high-level names here. So let Q1, Q0, 0, 0 be named as S0, 0, 1 be named as S1, 1, 0 be named as S2, and 1, 1 be named as S3. Similarly, let X0 be named as A and 1 be named as B. or you can leave it as 0, 1 itself. Z1 is Z0. Let Z1 is Z0. 0, 0 we named as P. 0, 1 we named as Q. 1, 0 we named as R. 1, 1 we named as S. Did you get that? Is that clear? 2-bit input. So I'm giving different names to that. Now substituting these names, let me come to the high-level state table. I'm trying to form the high-level state table now. You have the present state. Here write S0, S1, S2, S3. Right? X input taking the value A, B. Output Z taking the value what is 0, 1. What is that? 0, 1 is Q. 1, 1. 1, 1 is S. 0, 0 is P. 1, 0 is R. Right? Let me write the next states also. 0, 1, S1, S1, S0, S0, S2, S1, S2, S1. Did you get that? Using this substitution, I am rewriting the binary state table as the high-level state table. Now you have the high-level state table. What next? From the high-level state table, what should be the next step? State diagram. Yes, you have to draw the state diagram. So let me draw the state diagram. Four states, S0, S1, S2, S3. At each state I have got an output. Here it is Q, here it is S, here it is P, and here it is R, since it's a mode machine. Now from S0, if the input is A, it goes to S1. Input is B, it goes to S2. At S1, if the input is A, it remains in S1. At S1, it always remains in S1. If the input is A or B, it remains in S1. At S2, if the input is A, it goes to S0. If the input is B, it remains in S2. At S3, it goes to S0 or it goes to S1. Now, this is a typical example of two different types of states. Let me see. We have got an originating state and a terminating state here in this. An originating state means S3 is an originating state. You can see that the arcs get originated from it, but no other arcs are getting terminated in it. So such states are called the originating state. Once you leave that state, you cannot come back to that state. And S1 is a terminating state. Once you reach that state, you cannot go out of that state. Okay. So these are just certain terminologies used for the states. Now, after arriving at the state diagram, if you are able to find the purpose of that, then you will you find out the word statement corresponding to the given figure. If not, you will just leave it at the state diagram itself. Here we just drew some random circuit, so we are not able to find out the purpose of the circuit. So just leave it as such. So is the concept clear for this? How do you do the analysis? So given a circuit, you find out the word statement corresponding to that. That is called analysis. Okay. So let us go for the second example. Second example is, so this one, this problem 631, that you can do it as a homework. It has got a lot of gates at the input side. That's why we are not using it for this. Otherwise, when we come to the offline class, we will do it. Okay, we'll go to the example 651. Did you see that? Example 651. We'll try to do that. So, right, analyze the given sequential circuit. So let us try to do that. Hopping down the question, what type of flip-flops are you making use of? We are making use of JK flip-flops. JK. The flip-flop is named as A. Two outputs, Q, A. Then another JK. Flip-flop is named as B. There is an output QB bar, which is OR together to get your result. Right? Again, what type of machine is this? Is this a Mealy machine or a Moore machine? Having analyzed this part of the circuit, what type of machine is this?
Moore machine.
It's a Moore machine, isn't it? I mean, I didn't hear what you said, but I guess what you said is Moore, because the output depends only on the state. Okay. Let us go to the input part. This K comes from QB bar. This is QB bar. Sorry, QB only. That K is QB. And this J is QA. Isn't it? Maybe I will draw this one. Okay. Both are clocked by the same clock. So synchronous sequential circuit. And this K is from two inputs, which are the X and X bar, I guess so. X bar and QA bar, isn't it? That is X bar and QA bar, right? And the other J is from X bar QB bar plus XQA. Right? So this is the given figure. Now we'll try to write the expression. Output Z is equal to QA plus QB bar. Two flip-flops. JA is equal to X bar QB bar plus XQA. KA is equal to QB. JB equal to QA. KB equal to X bar QA bar. Right? So we are written the Boolean expressions. What next? You have to find out the number of inputs and the number of outputs and the number of flip-flops. Okay? Number of outputs. Outputs 1. Is it? Is it? Number of inputs 1 X, and we know that this output is it's a Moore machine, so that also will indicate it over. Number of flip-flops 2. Okay, what type? JK. So now we are going to draw the state diagram. We know that since there are 2 flip-flops, Q1, Q0, the present state will be 0, 0, 0, 1, 1, 0, 1, 1. Right? X input, taking the value and 0 and 1. Here I am going to write JAKA, JB, KB. Right? What is JA? JA, which we know that it's a function of what all? It's a function of QA, QB, X. So I'm here writing it as QA, QB. Instead of Q1, Q0, I have to write it as QA, QB. Right? Is that clear? I named it as A and B. So QA, QB. JA, which is a function of QA, QB, X is equal to X bar, Q bar plus XQA. So X is 0 here. So XQA will become 0, isn't it? I'm going to rewrite the expression here. JA, which is a function of QA, QB, X is equal to X bar, QB bar plus XQA. So when X is 0, this part goes 0. X is 0 means this X is 1. So it is QB bar. So what is QB bar? QB bar is 1, 0, 1, 0. Is that clear for JA? Now when X equal to 1, I'm going to rewrite the expression. This part goes 0. So it is QA itself. What is QA? 0, 0, 1, 1. So I have written JA for X equal to 0 and X equal to 1. Now I'll go for KA. What's the expression for KA? KA is nothing but QB always. So it is 0, 1, 0, 1, 0, 1, 0, 1, irrespective of X. So those are JKA. Now I'll write JBKB. What is JB? JB is nothing but QA. QA 0, 0, 0, 1, 1, 0, 0, 1, 1. Did you get that? JB is nothing but QA. And KB is X bar QA bar. So when X is 0, it is QA bar. 1, 1, 0, 0. When X is 1, it is always 0. Is this clear? Is this clear? Okay. Now we have JA, KA, JB, KB and the present inputs. If this is the present input and if the JK inputs are this, we are going to find out the next inputs. QA next, QB next. Let us find out QA next first. See, for this flip-flop, if the input is 1, 0, what will be the output? 1. Let me use this pen. 1. Did you get that? 1, 0. 0, 1. 0 always. 1, 0. 1. 0, 1. 0. Here. 0, 0. 0, 0. What does that mean? It retains the previous condition. Then you have to look for the previous condition for A flip-flop. What is the previous condition? 0. So that condition is maintained. This 0, you look at this, and that is being maintained here. 0, 1, it is always 0. 1, 0, it's always 1. 1, 1, see, 1, 1. 1, 1 for JAKA. So that means this 1, since it is 1, 1, it is being toggled and it becomes 0. Let me write it for QB then. 0, 1. 0, 1 is always 0. 0. 1, 0, 1. 1, 0, 1. 0, 0. Here it is 0, 0. What does that mean? Since this is 0, this also will be 0. 0, 0. Since this is 1, this also will be 1. 1, 0. 1, 1, 0, 1. Did you get that? Is this clear? How we wrote the next state. We know the present state and we know the JK inputs. So we write the next states. We find out the next states. The reverse process. Use the truth table for the flip-flops and find out the next states. Now, we don't require this. We don't require this part. We have the present state and the next state. Let me complete the truth table, binary table with my Z output. This is my input. This is my Z output. Z output, what's the expression? QA plus QB bar. So whenever QA is 1, it's going to be 1. Now it's or whenever QB is 0, this is going to be 1 here. So it's 0 only for this. Isn't it? QA 1, it's 1, or QB 0, it's 1. Okay. So this is the table that we require now. Present state, next state, and the output. So what next? What next? You have to give the high level names. There are 2 flip-flops, so 4 states. I'm going to give the state names. So we write it as the high level assignments. Instead of the binary assignments, we write it as the high level assignments. State QA QB 0 0, we name it as S0. 0 1, you name it as S1. 1 0, you name it as S2. 1 1, you name it as S3. Right? Let X and Z be in that binary form itself. So rewriting it, you can say that this is present state, S0, S1, S2, X3, X input 0 1, Z output 1 0 1 1. Then this is S2, S0, S3, S1, S0, S1, S3, S1. That's the next state. What next? You have to draw the state diagram. S0 with an output 1, S1 with an output 0, S2 with an output 1, S3 with an output 1. From S0 it goes to S2. There is 0 input. Or it remains in S0 with an 1 input. From S1 it goes to S0, 0 input, or it remains in S1 with a 1 input. From S2 it goes to S3, always 0 or 1. It always goes to S1, 0 or 1. Okay. We got almost the same circuit, isn't it? Here S3 is the terminate, so oh no, S1 is the terminating state. No, S1 is also not terminating. No, it's not the same circuit. Okay. None of the states are terminating because there are arcs coming to the circuit and coming to the state and leaving the state as well. Is this clear? Are we able to figure out some purpose for this? No. Okay, so we'll leave it at that point. I'll do some exercise problems as well. We'll go to figure E68. Figure E68. Is this clear? Any more explanation required for this?
No, ma'am.
Okay. Now do figure E68. Shall we do that? Copy down the circuit. How many flip-flops are there? 2 flip-flops, right? It's a bit tricky question. T flip-flop and another T flip-flop. Both are clocked by the same clock. Q1 output. So this is flip-flop 1 and this is flip-flop 0. Q0 output. Q1 output goes to the enable of a decoder. With Q0 outputs to its 0 input and the 1 input connected to X2. And the decoder has got, that's a 2 to 4 decoder, 4 outputs. 0 is a Z1 and 1 is a Z0. Right? Now looking at the output circuit, output combinational circuit, can we say what type of machine is this? Is this a Mealy machine or a Moore machine?
Mealy machine.
It's a Mealy machine because the output depends on the input X also. Okay. How many output bits are there? 2 output bits, Z1 and Z0. Okay. And the input point, we have got mux. Four is to one mux, whose control lines are connected to X1 and Q1, isn't it? X1 and Q1, and the data lines are connected to 0, 1, 2, 3, Q0, X2, 0, 1. That goes to T1 and it is Q1 bar that comes to T0. Right? How many input bits are there? How many input bits are there?
2.
2 input bits, isn't it? X1 and X2, right? 2 output bits Z1 and Z0, 2 flip-flops with Q1, Q0 as outputs, right? Now let me write the expression. Can I write the expressions for this? It's not possible to write the Boolean expressions because the C1, C2 blocks are not done by using logic gates. It's done by using standard modules, isn't it? So we have to directly go to the state table. We are not able to write the expressions here, right? So here we'll go for the state table. So before that, number of flip-flops 2, Q1, Q0. Number of outputs 2, Z1, Z0. Number of inputs 2, X2, X1. Isn't it? X0 undo, evidengilum undo. X0 ningal ee figure il evidengilum kandayirunno? Illalla. X2, X1. So that's it. So we're going to draw the binary state table. Q1, Q0, present state, X input, X2, X1. So 4 combinations possible, 0, 0, 0, 1, 1, 0, 1, 1. Did you get that? Here we are going to write the 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. Here we are going to get the T1, T0 values. Right? Okay. What is T1? Let us look for T1. T1, which is a function of Q1, Q0, X2, X1. T1 is a function of Q1, Q0, X2, X1. Did you see that? So the first point here, X2, X1 is 0, 0, Q1, Q0 is 0, 0. That is Q1 is 0 and X1 is also 0. So 0, 0. So it will look for Q0. What is Q0 at that point? Q0 is 0. So you'll get it as a 0. Did you get that? How did we get that? We know that T1 is a function of Q1. This is Q1. This is X1. This is Q0. And this is X2. It's a function of q1, q0, x2, x1, right? All the 4 variables. Now we'll look at this point. At this point, we know that x2, x1 is 0, 0, q1, q0 is 0, 0. Correct. So q1 is 0, x1 is 0. So this is 0, 0. So that means the first input will come to the output as t1. What's the first input? q0. q0 means it is, look at the value of q0, it is 0. We'll go to the second point, where x2 is 0, x1 is 0. x1 is 0, q1 is 0, and q0 is 1. So this is again 0, 0. This is again 0, 0. But q0 is 1. So this goes 1. Now this is 1, 0. x1 is 0. This is q1. This is q0. x1 is 0. q1 is 1. So it is 0, 1. It will just copy x2. x2 is 0. Now this here also, x2 is 0. x1 is 0. And q1 is 1. So 0, 1. So it will copy x2. x2 is 0. Did you get that? You have to find out the values by giving the different values from these table to these inputs and then get the value of t1. Now fill the table. x2 is 0. x1 is 1. So x1 is 1 always here. In this column, x1 is 1. Now q1. q1 is 0. 1, 0. 1, 0. That means this input. So 0, 0. And q1 is 1. 1, 1. That means this input. 1, 1. Here. x1 is 0. x1 is always 0. And then q1. q1 is 0. So 0, 0. So it will get q0. q0 is 0. q0 is 1. Here x1 is 0 and q1 is 1. 0, 1. x1 is 0, 0, 1. x1 is 0 and q1 is 1, 0, 1. It is x2. That is 1, 1. Right. Then 1, 1. x1 is 1. q1 is 0, 1, 0. That means 2. It is always 0. 1 and this is 1. So it's always 1. Find out T1 from this. Now we have to find out T0. What is T0? T0 is always Q1 bar. So 1, 1, 0, 0. 1, 1, 0, 0. 1, 1, 0, 0. 1, 1, 0, 0. Did you understand this? How we wrote the values for T1 and T0 by analyzing the logic block mux and giving the different values of Q1, X1, Q0, X0, X2.
എക്സ്പ്രഷൻ എഴുതണം നിർബന്ധമില്ല, ഇത് അറ്റൻഡ് ചെയ്താൽ മാത്രം മതി.
കേൾക്കത്തില്ല, ഇവിടുത്തെ സ്പീക്കർ ശരിയല്ല. അപ്പം ഒന്ന് ഒരു മിനിറ്റ്, ഞാൻ ഫോണിൽ പറയാം. ആയിട്ട് പറയാം.
11.
Can you hear?
T1 expression എഴുതി ഒന്നുകൂടി പറഞ്ഞല്ലോ.
Okay. Okay. Am I audible? Can you hear? Okay. Now listen. See, T1 is for this point. Let me check for this. Okay. That is when Q1 is 0, Q0 is 0, X2 is 0, X1 is 0. Right? So I'm putting X1 value as 0, Q1 value as 0. Right? 0, 0. X1 is 0 and Q1 is also 0. 0, 0. Then it selects the first value of the multiplexer and that is routed to T1. Select. What's the first value of multiplexer? Q0. So Q0 is 0, so this is 0. Did you get that? Is that clear? How we got the first value of T1? Q0 is 0, so we get it as 0. The next point, Q1 is again 0 and your X1 is also 0. So it's again 0, 0 here. So it takes Q0, but here Q0 is 1, so you get it as 1. Right? Now here, X1 is 0, but Q1 is 1. So see, it is 0, 1 here. 0, 1 means it takes the second input as the output. What's the second input? X2. Any doubts?
Clear ആയി man, clear ആയി.
Okay. Ampare, the doctor. Any doubts? Clear. Okay. Now, at this point, it is 0, 1. So I get the value of X2. What is X2 here? 0. So I write the value of X2 here. It is the X2 value that comes here. And here as well. Clear? Similarly, put different values of X1, Q1 and see how these inputs will come to T1. Is it clear? Okay. So now we reach this point. So you have the present state and we have the T1, T2 inputs also. Now we have to get the next states, that is the Q1 next and the Q0 next for the different X2, X1. We have to get that. See, let us look for T1. Currently it is at 0. and your Q1 state is 0. Q1 is 0 and your T1 is 0. So next state will be 0 itself. The T1 is 1. So this toggles to 1. 0. So it copies that. 0. So it copies that. This one. 0. So it copies. 0. So it copies. 1. So it toggles. 1. So it toggles. 0. So it copies. 1. So it toggles. 1. So it toggles. 1. So it toggles. 0. So it copies. 0. So it copies. 1. So it toggles. 1 again. So it toggles. That was for T1. Now let us look for T2. T0. So you have to look for Q0. To 0 here. 1. So it toggles. 1. 1 toggles. 0. Same as 0. 0. Same as 1. 1 toggles. 1 toggles. 0. Same as 0. 0. Same as 1. This 1 toggles. 1 toggles. 0. Same as 0. 0. Same as 1. 1 toggles. 1 toggles. 0. Same as 0. 0. Same as 1. So now we have the present state and the next state. Is this clear? Is this clear? Okay. Now we have to create a similar table for the output. Let me draw one for the output also. Actually, we have to write it as comma over here, but since that becomes too crowded over there, we are going for another table with Q1, Q0, present states, 0, 0, 0, 1, 1, 0, 1, 1, x2, x1, 0, 0, 0, 1, 1, 0, 1, 1. I'm going to write Z1, Z0. Right? From the decoder, since the Z1, Z0 outputs are the two decoder outputs, both can never be ones. They can be zeros, both can never be ones. Isn't it? Okay. See. Now for the decoder is enabled only when Q1 becomes 1. Right? So for the first row and the second row, Q1 is 0. What does that mean? I can keep the Z1, Z0 output to be 0, 0. Did you get that? Because this is enabled by Q1. Since Q1 is 0, that's not enabled at all. So all the outputs will remain at 0. Is that clear? The first two rows of Z1, Z0. Okay. Now, the last two rows means Q1 is 1. So this is enabled. Now it depends upon X2 and Q0. So here X2 is 0. Q0 is 0. So that is 0, 0. 0, 0 means Z1 must be 1, but Z0 will be 0. Here also X2 is 0 and Q0 is 0. Again 0, 0. So 1, 0. Here X2 is 1. X2 is 1 and Q0 is 0. So it is 1, 0. Did you get that? X2 is 1 and Q0 is 0. 1, 0. 1, 0 means 2. Right? So this will be 0, 0. This is also 1, 0. 2 will be selected. So these two will not be selected. Now, for this point, X2 is 0, Q0 is 1. So it is 0, 1. So Z0 will be 1 and this will be 0. Here also X2 is 0 and Q0 is 1. So it is 0, 1. So it is Z0 that goes 1. Then again X2 is 1 and Q0 is also 1. So it is 1, 1, that is X3 is selected. So this will remain 0, 0. Here also X2 is 1, this also is 1. So this will remain 0, 0. Clear? Is this clear? Is this clear? When the output goes to the decoder 2 output and the decoder 3 outputs, both Z1 and Z0 will remain 0. And when it is not enabled also, it remains at 0, 0. Now the next step is to give the high level names. So giving the high level names. So let us give some high level names like state, Q1, Q0, 0, 0 is S0, 0, 1 is S1, 1, 0 is S2, and 1, 1 is S3. Similarly, input, X2, X1, 0, 0, let it be A, 0, 1, let it be B, 1, 0, let it be C, and 1, 1, let it be D. Now the output is Z1 is Z0, 0, 0, let it be P, 0, 1, let it be Q, 1, 0, let it be R. That will be enough. It can never be 1, 1. So 1, 1 combination doesn't occur. Okay. So using this, I'm going to rewrite the state table. Present state. I'm going to combine these two tables. This is not needed now. This part and this part can be combined. S0, S1, S2, S3, input X, A, B, C, D. Here I am going to write next state, comma, Z. Right? So let me write the states first. S1, S2, S2, S3, S1, S0, S0, S1, S1, S2, S0, S1, 0, S1, S0, S0, S1. Okay. Comma. I'm going to write the output. And then A, 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 P, sorry. P, put in the variable. P, here it is Q, R, 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 P, P, Q, Q, P, P. Is this clear? Now we draw the state diagram corresponding to it. S0, S1, 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 S1. With an output P. S1, S2, S0, S2, S0. S2 for A and C with an output P. S0 for B and D with an output P. Then S2, S0, S0, S0. It remains in S2 for A with an output R. Goes to S0, B with an output R, C comma D with an output P. At S3 it remains in S3 with an output Q, or it goes to S1, B with an output Q, and C comma D with an output P. Okay. So these are some sample examples. That's why we are not getting we are not able to get to the state. Sorry, the word statement. Now let me ask. Suppose there are while designing a circuit, there are three inputs to a circuit. Right? And the number of states, or let us see that there are three. You're designing a pattern recognizer that recognizes a 3-bit pattern, 0, 1, 1. How many states will it have? How many states? Put in the chat box. If you're designing a pattern recognizer which has got a 3-bit pattern, how many states will it have? 3 states, right? Okay. Now, how many flip-flops do you require to design it? 2 flip-flops. So, this 2 flip-flops figure when you get, and when you try to analyze it back, we will analyze it with 4 states. Is that clear? Did you understand that? Say, suppose we design a flip-flop, a pattern recognizer that recognizes a 3-bit pattern. We make use of 2 flip-flops over there. We have the figure with 2 flip-flops over there. Now try to do the analysis of that. We take 4 states over there and analyze, isn't it? Right? So it is not always necessary that we always reach the same point where we started with. That's because of that redundancy over there. We put it as don't cares and make use of those don't cares also, isn't it? So that is also incorporated in the design. And even if you are not making use of the don't cares, we put it as zeros over there. The unused ones. Okay. So let us go for the next one also before we stop. We'll do one more example. Okay. Shall we go ahead? One more example? Or is it time to stop?
Ma'am, it is time to stop.
It's time to stop. I didn't hear it. Put it in chat box. Your classes started at 9. Okay, I'll leave those two as homework, but I'll just give you some hints in doing it. Go to question 618. 618. That is figure E69. Okay. Now looking at that, we can see that there are 3 flip-flops, out of which 2 are JK and 1 is SR. So the analysis has to be done according to that, right? And how many inputs are there? There is 1 input X and only 1 output is it. Now look at the next figure. That is question 619. How many flip-flops? Only 2 flip-flops. Both are T flip-flops. That is okay. Is there an output? Is there an input? There is no input and output over there. So the output can be taken as the state itself, and the input is that means whatever be the input state. There is no input at all. So it doesn't depend upon an input factor X. Suppose if there is an input factor X, for the input X equal to 0 and X equal to 1, it has got the same present state to next state transitions. That means it doesn't depend upon that input X. It's just like a counter. Whenever it gets a clock, it moves ahead. So try analyzing that circuit also. Okay. So we'll review that in the next class. Monday also we'll have a 2-hour session. Okay then, thank you. So if you have any doubts, you can contact me anytime. I'll be here for a few minutes to clear the doubts. Class reps, please send me the attendance.
Yes, miss.
Thank you.
Thank you.
Thank you, ma'am.
One second. Hello, can you hear me?
Yes, ma'am.
Yeah. Siddharth, you're trying to ask something? Okay then. Thank you. If you have any doubts, you can call me anytime.
ഒരിക്കലും എനിക്ക് ചേട്ടായില്ലേ
और मेरा घंटा बढ़ेगी तुझसे शुरू करो
എന്റെ സ്വന്തം അനുഭവം എന്നൊക്കെ പറയാം. പ്ലസ് ടു പഠിക്കുന്ന കാലഘട്ടം അന്ന് പഠിക്കാൻ പാടായതുകൊണ്ട് ഞാൻ അടുത്തുള്ള ഒരു ചേട്ടായിയുടെ അടുത്ത് ട്യൂഷന് പോയി. എന്നും ഞാനും ചേട്ടായി മാത്രം. ഒരു മണിക്കൂർ ഒരു മുറിയിൽ കയറിയിരിക്കുന്നു. സത്യം പറഞ്ഞാൽ എന്നേക്കാൾ വലിപ്പമുള്ള എന്റെ മാറുകളും ചന്തികളും you.